fundamental quantities. Okay, there are about 7 of them, but we are going to be working with these 3 for now. So the fundamental quantities are the ones that stand on their own. Okay, other ones are derived using these fundamental quantities. So now we have mass, we have length, and we also have time. So this one now we are going to see how they are used in order to derive other formulas. Now let's start with velocity. Now we know that velocity is represented by letter V. And velocity, the formula we know that is the distance covered in a particular time. Okay, so the formula is distance over time. So this is the formula for velocity, distance covered in a particular area all over the time taken to cover the distance. So now, this distance, you know that distance is taken as moving like from point A to point B. Okay, so if you move from point A to point B, you have covered a particular distance. So this point A to point B is the same thing as length. Okay, this particular quantity. So this is the same thing as length. And because of that, we can represent distance as length. So this we can write it as L, which is our length. Okay. Then time, already our time is already here. So because it's already here, we just write it as represented by a capital letter T. So we write it as T. Alright? So from here now, I can be able to say that this is my L. So I'm going to bring this T up here. If I bring T up here, it's going to be the inverse of T, okay? So this will become T inverse. So this is the dimension for velocity. So we have derived the dimension for velocity. In case they ask you to derive the dimension for velocity, this is it. Now that we have derived for velocity, let's also derive for acceleration. Now we know that acceleration is represented by letter A, okay? Now we know that the formula for acceleration is velocity the velocity of that particle all over the time taken, okay? So the formula for velocity and for acceleration is velocity all over time. Now from what we have just did here, we know that our velocity, the dimension for velocity is L T inverse, okay? So because of that, I can be able to just write this one now. Instead of driving it again, I will just impute this one as L T inverse all over time. Now we know that our time is T, so we just impute it here. So this will now become, so what I'm going to do, I'm going to carry this particular T up just like the way I did here. And if I carry it, it's going to also become another T inverse. So this is the same thing as L. I have this T inverse, then if I carry this one up, it will be multiplied again by another T inverse. Now I have 2T inverse, okay? So if I multiply this 2T's, it's going to become T squared. T inverse squared. So this is going to become L T. Now this and this will be minus 2 inverse. And so this is the dimension for acceleration. So that's how we draw the dimension for acceleration. Now let's also draw dimension for force. Okay, let's see how we can draw the dimension for force. Now force, given the letter F, is the same thing as mass times acceleration. Okay. Mass times acceleration. So because mass is the same thing as mass times acceleration, we know from our fundamental quantity, mass is represented with capital letter M. So I can write this one as capital letter M. Then acceleration, I have drawn acceleration here as L T inverse square, okay? So I can just write acceleration as this, which is L T inverse. So this is just the dimension for force, as simple as that, okay? Now the next one, again, let's also see how we can grab a dimension for pressure. Now we know that pressure is represented by letter P is the same thing as force all over area. Pressure, the formula for pressure is force all over area. Now, you can see that we've already derived the formula for force, which is MLT inverse square, okay? So, because of this, we already know what is our force, which is by T. So, we just carry this one and impute it here, and it become our force. So, we say this is also equivalent to this, which is M L T inverse all over. Now, area. Remember, area is the same thing as length times breadth. Length times breadth. Remember, all there are two things. There's length. Okay, the length. Let's say the length of the square. The area of the square is length times breadth. Okay. So there are two things here. This is a distance. This is also a distance. So there are two L. So because of that, the dimension for area is going to become L squared. Okay, because there are two lengths. There is the first length, there is the second length. So it becomes two lengths. So that's why the dimension for area will become L squared. Okay. So now I'm also going to carry this L up here, just like the way we did with these other ones. So if I do so, I'm going to have M L T inverse square. Then multiply by this one that I'm going to carry it up, which will also become L inverse square. So now, from here you can see that I have another L here. So I'm going to actually combine the two so that it will become one. Now if I'm combining, multiplying this L with this L, remember this one is the same thing as L to the power of 1. Okay, so it's like I'm adding 1, okay? And then I have minus 2. Remember, when you are multiplying this, you use the laws of indices, okay? So you are going to add the power. So this is the power of 1, this is the power of minus 2. So it will become like 1 minus 2. And 1 minus 2 is the same thing as minus 1. So that means the value of my L is going to become M minus 1. Because this one now, we have 1 here and we have minus 2. 1 minus 2 is minus 1. So that's why my L becomes minus 1. And then I will put the value of also my T squared. So this actually becomes the dimension for pressure. Okay? So that's how we drive the dimension for pressure. Now the next thing, let's see how we can drive the dimension for work. Okay? Let's see how we can drive work. Now we know that work, given by letter W, is the same thing as force multiplied by distance. Okay, the formula for work is force multiplied by distance. So because this is the formula for force. Now for work. Now we've already derived the dimension for force. If you look at our work here, this is the dimension for force. So we'll just use it as M L T inverse multiplied by distance. Remember, distance is the same thing as length. So this one now will become L. Okay? So because of this, we have two L now. So we are going to combine these two. L times L will now become L squared. So we have M L squared T inverse squared. So this becomes the dimension for work. Okay? This is the dimension for our work. Now again, let's just check one more dimension. Let's check for power. Okay? So power, given as letter P, okay? Now, we know that power, the formula for power is work done all over the time taken, okay? Power is work done all over time taken. So power is work all over the time taken. So because we already know what is the dimension for work, which is actually this one, okay? You can just carry this one and impute it here, and then we have this is m L square G inverse square all over time. Remember, time is letter T, okay? So from here, we can also carry this T up so that you come and meet with this one. So this becomes M L square T inverse square multiplied by another T that's coming up. So if you multiply these two T, remember we are going to just add the powers according to indices. So we have minus 2 and then we have plus 1. This is the same thing as the power of 1. This one is minus 2. So if we add minus 2 plus 1, it will be the same thing as minus 1. Okay? So this is going to be what we have here. So because of that, we have M L squared then T inverse. So okay, because these powers, these T multiplied together will become minus 1, because one of the T here will be deducted from this one. We have minus 1 here. So this is the formula for power.